Okay, so let's do some Thévenin equivalent circuit examples. So let's start with this one. So what happens if you have a circuit that has a dependent source in it? So we said we can use the quick method as long as our circuit network has only independent sources. But what happens if we have a dependent source? So let's look at this example. So we have a 2Vx voltage source. So this is a voltage controlled voltage source. We have a 6 ohm resistor. We have a 3 ohm resistor. We have the 8 amp source. We have the 10 ohm resistor. We have the 15 ohm resistor, and we have the 20 volt source. Here is the voltage Vx, the voltage that controls that 2Vx source. And here's the current Ix that we're actually solving for through the 3 ohm resistor. Now I want to make a point here. We are going to find Ix using a Thévenin equivalent circuit. But what if you were asked, or what if you wanted to find the voltage Vx using a Thévenin equivalent circuit? Okay, it gets a little dicier when we have a dependent source in the circuit, because the dependent, the dependent source and the element that controls it both have to be in the circuit network, or they both have to be in the load. Okay, so if you want to solve for Vx here, this voltage Vx, since it controls that dependent voltage source, they both have to be in the load, and that's hard to do. Okay, so be very careful about that. So for this circuit, though, we're going to solve for Ix. So in that case, the 3 ohm resistor is going to be our load, and the 2Vx source and its controlling element will both be in the circuit network. So let's start by drawing that circuit network. We're going to have the 20 volt source, the 15 ohm resistor, the 10 ohm resistor, the current source, 8 amps. We're going to take out that 3 ohm resistor, taking care to maintain the terminals. That's always important. We have our 6 ohm resistor, and then we have that dependent voltage source. Here is Vx, and this is going to be our open circuit voltage across the terminals that we removed the load. So remember, you can solve for this circuit using any method that you like. I'm going to use mesh analysis here, mainly because we have this kind of unique situation that we haven't seen before, so I want to make sure to go through it. So I've got a mesh current I'm going to call I1 here, and then I've got this big mesh that goes all the way around here that I'm going to call I2. Okay, what we're going to find is we're also going to have a little bit of what I call a submesh. So we're going to write this entire mesh equation around this whole part of the mesh, and then we're going to write a little submesh around this part that includes that open circuit voltage. And we can actually do that submesh on this side of the open circuit voltage terminals or this side. The answer will be the same. All right, so let's start though with just this plain mesh analysis. So what do we know? Well, we know that I2 is equal to -8 because the current source is flowing opposite our mesh current. And then we also know what Vx is. Whenever we have a dependent source in the circuit, we know something about at least the controlling element. So Vx is equal to, by Ohm's law, 10 times the net current that flows from plus to minus. So I2 flows from plus to minus, I1 flows against. So our net current is going to be I2 minus I1. Multiply that by 10 and we have that voltage. Okay. Now, in order to find the mesh current I1, we only need mesh equation 1. So that's going to be minus 20, moving from plus to minus, minus 15 times I1, minus 10 times I1 minus I2. Remember, I don't care about Vx for writing this technique. All right. I'll substitute I2 into this equation, and I can solve for I1. And when I do that, I'll get that I1 is equal to minus 4 amps. Okay, so I know mesh 1 current, I know mesh 2 current. Now I need to find I need to find VOC. Okay, before I do that, let's go ahead and solve for Vx because we're going to need that. And so when I do that, I'm going to get that Vx is equal to, substituting I2 and I1 into that expression, we'll get that Vx is equal to minus 40 volts. Okay, so now the submesh, and I'm going to draw just a little loop here. Okay, and so the submesh, I'm going to let VOC, this voltage here, represent everything that's going on this side. Okay, so my submesh, starting with VOC, and I'm just really writing a small KVL loop within the mesh. So it's going to be VOC minus 6 times I2 minus 2Vx is equal to 0. All right, I'm going to go ahead and substitute in I2 and Vx into this equation. And I'll get that VOC is equal to minus 128 volts. And don't let a large voltage throw you. I don't normally do a whole lot of checking to see if any of this stuff makes sense from a practical standpoint, the values at least. Okay, so there's our open circuit voltage. Now, remember, this is different because we have a dependent source in our circuit network, which means we cannot use the quick method. All right, so we're going to have to must use long method here. Okay, which means we're going to take that circuit network again. I'm going to draw it out again. So here's 2Vx, here's 6 ohms, 8 amps, 10 ohms, the voltage Vx, 15 ohms, and 20 volts. Okay, but so for the long method, we're going to take our terminals and we're going to short them together and solve for the short circuit current flowing through that short we just created. Okay, and again, we can use whatever method we like to solve for this particular circuit here. You could do mesh analysis, you could do nodal analysis, although nodal analysis is tough. Let me take this back. When you are solving for short circuit current, you're almost always going to use mesh analysis here. Okay, so let's talk about that. So we're going to have I1 here, we're going to have I2 here, and we're going to have I3 there. Okay, so let's talk about what we know. All right, so what is ISC? We need to solve for ISC. So what is ISC? Well, ISC is equal to the current flowing in the direction, which is I2, minus the current flowing against, which is I3. So ISC is equal to I2 minus I3. All right. What about, what else do we know? We know that I2 is equal to minus 8 amps. We know that Vx is equal to 10 times I2 minus I1. That really hasn't changed from the previous circuit. Okay. So now we can write our mesh equations. So mesh 1. We have that, so we have minus 20, minus 15 times I1, minus 10 times I1 minus I2 is equal to 0. Just like before, we don't care about Vx for writing down the technique. Mesh 2 we don't need, because we know what mesh 2 is. It's minus 8. Okay. Mesh 3 we need. Okay. So as we go around here, there's no voltage here. This is a short circuit, so there's no volts here. So we're going to go up to the 6 ohm resistor. So we're going to have minus 6 times I3 minus 2 Vx is equal to 0. Okay? There's nothing here. There's nothing here. All right? This is a short circuit. There's no voltage there. Don't try to make this something that doesn't exist. Okay? Sorry. Okay, so we're going to substitute in the things that we can here. So this mesh 1 equation is going to be minus 25 I1 plus 10 I2 is equal to 20. All right. The mesh 3 equation, this is going to be minus 6 I3 minus 20 times I2 minus I1 is equal to 0 when we substitute in Vx into that expression. And so the mesh 3 equation will become 20 I1 plus 20 or minus 20 I2 minus 6 I3 is equal to 0. We'll substitute in that I2 is equal to minus 8 in both cases. All right, and so what we'll be left with is that I1 is equal to, please hold. Is equal to minus 4 amps. I2 we already know is minus 8. And then I3 will be, for some reason I don't have I3 written down. Hold on a second. Hold on. Is minus 13.33 amps. Okay, and so when all is said and done and we solve for ISC, remember ISC is I2 minus I3, we're going to get that ISC is equal to, nope, something's not right. Please hold. I'm sorry, hang in there for a second with me. Hang in there. I think I've got a math error somewhere. Just bear with me for a second. This is going to be plus. Yeah, this is going to be plus 13. That's why. That's going to be plus 13.33, not minus. Okay, so now ISC is equal to I2 minus I3. So this is going to be minus 8 minus 13.33. So now ISC will equal minus 21.33 amps. My apologies for that error. I just couldn't see it. Okay, so now we've solved for ISC. And remember what I said when we talked about the long method back in the concept lecture. The Thévenin equivalent resistance in this class is always going to be positive. So your open circuit voltage and your short circuit current have to have the same sign. So the open circuit voltage is negative, and so is the short circuit current. If you get those to be opposite in sign, you need to go back and either look at how you labeled ISC relative to VOC, or you need to go back to your math and figure out where you made a math error. Okay, so we can solve for the Thévenin equivalent resistance now. Our Thévenin is equal to the open circuit voltage divided by the short circuit current. This is minus 128 over minus 21.33. So the Thévenin equivalent resistance is going to be 6. So if we draw our Thévenin equivalent circuit, this is going to be 6 ohms, our Thévenin equivalent voltage source. This is going to be minus 128 volts, our Thévenin equivalent voltage source. And I think I said Thévenin equivalent source. I meant, let me just repeat that. So we've got minus 128 volt Thévenin equivalent voltage source. 6 ohms is our Thévenin equivalent resistance. Then we are adding back in our original load, which was the 3 ohm resistor. Okay, and we were solving for this current here, IX. Okay, and so IX is going to equal minus 128 divided by 9. And so IX is going to be minus 14.22 amps. Okay, just a reminder that forget about the sign on this voltage for a second, on the voltage source. The current is flowing from minus to plus through the source, so it will flow from plus to minus through the resistor. So the passive sign convention is holding. We don't have to worry about changing the sign on the current here. All right, so IX is equal to minus 14.22. Okay, I'm only going to work one example here because we have one more concept to do, which is to use the Thévenin equivalent circuit for maximum power transfer, and I'll work a whole bunch more examples with that, but we'll be designing for the resistor as well as solving for voltage and current. So look to those examples for more examples on Thévenin equivalent circuits.